Let us continue our discussion on neural network and the optimization of the weightages. Before we move to the next slides, let's just revisit again the last slide that we discussed in the previous video, just to make the story flows. Then, so if you still remember last time, we discussed on how we optimize a simple single net. So as you can see in here, I have a simple single net with one input with a weightage of W1 and a bias of W0 there and an output Y. If there is an activation function, of course, then Y will be equal to the activation function with an input of the output from this node. So if the activation function is A, then the output Y will be function of A for W0 plus W1 times X. So this will be a model. And then if we want to use this model to capture a data, an output of a experiment, let's say an output data set T, expectedly if this neural net can model the data perfectly, so the output of the data should be equal to the output of this model. And let's say if the output in the data is equal to T, so if this model is perfect, then the error will be 0. T should be equal to Y. So the error can be expressed by this function. If Y is equal to T, then the error will be 0. The objective to optimize the weightage W0 and weightage W1 is by using the gradient descent method that we have already discussed before. So initially, the first step, you just have to guess the weightages W0 and W1, pick a number for it, and then we iteratively update it by taking an update factor delta W for W0 and W1. Where of course the delta Wi, let's call it Wi for, in this case, I is IR0 and 1. The delta Wi then will be proportional to the negative of the first derivative of the error with respect to the corresponding W, with the factor of alpha here, where alpha is the learning rate, how fast we expect the update of the weightage there to converge to the optimal weightage. So in this case, then again, if let's say error is expressed by this function, then the first derivative of error with respect to W, then it will be equal to 2 times half times T minus Y times the first derivative of Y with respect to W times minus 1, of course, because we have a negative Y in here. So the first derivative of error with respect of W will be expressed by this equation. This is just a simple chain rule of the derivation function. In a case where we don't have activation function, so we have only linear activation function where the output of the activation function will be equal to the Z itself, the input to the activation function itself, and Y then, the output Y then will be equal to this. So this term, the last term, here, the first derivative of y with respect to wi will be equal to the x itself. Of course, for w naught, then the first derivative of y with respect to w naught will be equal to 1. The first derivative of y with respect to w1 then will be equal to x in our case here. But to make the equation to be general, so I just express it with xi here. In case you have more than one input, then you might have x1, x2, x3, and so on and so forth, while x naught then corresponds to a unity value, which corresponds to the weightage of the bias here. Okay, so again, then if we neglect the activation function, the nonlinear activation function, if we just consider this net to have a simple linear activation function, then the updating factor of our weightage will appear like this. In the case that we need to consider the activation function, of course, we have to consider the first derivative of y with respect to weightage, and we have to consider the activation function in this derivation. But let's take a simple case for time being. Let's just consider a simple case when we have a linear activation function where a z is equal to z itself. Let's take a look on this example. I will take an example here, but let's consider a simple single network of Adeline network. So what is Adeline network? Adeline network is a concept actually to update the weightage, but the update is taken from the output of the node before the activation function. So in this case, the update of the weightage here will not consider the activation function, even though you have a nonlinear activation function, but the updating task will just consider a linear function in the activation function. So this will resemble to the case of this, where the linear activation function is equal to az equal to z when we are going to update the weightage. So this is how Adeline networks will update their weightage. They just update it from the output of the node before the activation function. Let's take a look in more detail from examples. Okay, now this is an example of, again, an AND function and logic function there, but I have bipolar input here, one, so I have 1 and -1 here. And then I will optimize the weightage here by using Adeline approach. So obviously, if you have an logic function, the network should have activation function here, because you need to round up the output to be 1 or -1. So there must be a nonlinear activation function in our network here. But we are going to update the weightage here using Adeline rule, in which Adeline rule will not consider the nonlinear activation function in updating their weightages. So let's try to update the weightage and optimize the weightages there. This will be the network that I will use to capture this AND logic function. So I will have two inputs, x1 and x2 here. I have W1, W2, and I have B here. Well, normally I use W not for the bias, but in here, just to differentiate with W, then I will use B for the bias. So I have three parameters here, W1, W2, and B. For time being, I still don't know what is the optimal weightage of this network to capture this AND logic function. So at the beginning, I will just grab it from the air. I will just, for simplicity, I will just assign 0, 0, 0 for W1, W2, and B respectively. These are the target. So if I have input 1, the second input 1, the target output should be 1. If x1 is 1, x2 is -1, their target output should be -1, and so on and so forth. So these represent this table represent the AND logic function. But now let's try to calculate the output of this network by assuming this weightage that I just grab it from the air, 0, 0, 0. So based on this network, then y will be equal to W1 times X1 plus W2 times X2 plus B. So the output of Y here before the activation function will be equal to 0 times 1 plus 0 times 1 plus 0, which is equal to 0. Now I will use this output of this network again before the activation function. So the output at this point to update the weightages. I will update the first weightage W1 here as what is discussed in the delta rule here. If we just consider a linear activation function, how we update the weightage is by taking the old weightage plus this factor, right? This factor is consisting of the learning rate times the difference between the target and the output of the networks times the corresponding input. So I will use this technique. I will consider a delta rule with a linear activation function here. So I will exactly do the same thing. I will update the W1 by taking the old weightage of W1, 0, plus the learning rate in here. I will just set the learning rate equal to 0.1 times the target. For time being, the target is 1. For the first data set, I will just update it from the first data set first, minus the current output is 0. So 1 minus 0 times the input for that weightage in the first data set, which is 1. It's equal to 0.1. So my new W1 now is 0.1. I will update it also for the second weightage, W2. Same thing, I take the old weightage of W2, 0, plus the learning rate, 0.1, times the difference between target and the output, 1 minus 0, times the corresponding input for the first dataset that we use to train this network for time being. It will be equal to 0.1 again. So W2, the new W2 will be equal to 0.1. I still have to update for the B, for the bias. I do the same thing, the old bias here, plus the learning rate times the difference between the target and the current output, and times 1, basically. Why 1? Because 1 is coming from the bias. So this will be equal to 0.1. So after this first iteration, I will have 0.1, 0.1, and 0.1 for W1, W2, and B. Now I will continue the training because I still have an error, obviously. the target is 1, the output is 0, so I still have an error. So I continue the training there, but now I will use the second data set, 1 minus 1 minus 1. So the target is minus 1 now. I will take the second iterative. So I calculate the y, the output of this network for these two input, the two inputs from the second data set. W1, the current W1 is 0.1 times X1 is 1 plus the current W2 is 0.1 as well times the second input of the second data set minus 1 plus B. Supposed to be a positive 0.1 here. So sorry for this, but this should be positive here. So it will be equal to 0.1. Then I will update again the W1. Same thing like before, I use the current W1, which is 0.1 times the plus the learning rate times the difference between the target and the current output. The current output is 0.1 now, so the target now is negative 1. So it will be negative 1 minus 0.1 times the first input on the second data set times 1. It will be equal to negative 0.001. I will do the same thing. I will update the W2. It will be equal to the old W2 0.1 plus the learning rate 0.1 times the target output minus 1 minus the current output 0.1 times the second input on the second data set minus 1. It's equal to 0.21. And then I do the same thing for updating the B. And the result will be 0 minus 0.01. So the current weightages of W1, W2, and B now are equal to negative 0.01, 0.21, and negative 0.01 respectively. I do it again for the third data set. And then I update it. I do the same calculation. And then at the end, I will get, you can try it by yourself, I will get W1, W2, and B equal to these three values respectively. Apparently, I still see an error there. I update it again for using the fourth data set. I will get this weightage. You can check it by yourself whether this has converged or not. How to check it? You just have to use all of these four data set to check whether if we are using these weightages, we will get a consistent output target. Of course, the output of this network that you have to compare to the target is the output after the activation function. So after you calculate the output here, you pass it to the activation function and then you compare it to the target. If it is the same, then that means your weightage has converged to the optimal weightage. So apparently these three weightages have already converged to the optimal weightages. So using these weightages, W1, W2, and B, I can calculate the output using this linear expression, and then after I pass this output of this node to the activation function, indeed I will get a consistent output here. 1 minus 1 minus 1 minus 1. It's exactly the same with the target. So to check whether your result has already converged or not, you have to compare the actual output, the output after the activation function with the target. If you get the same result the same values there, then that means your weightage has been converged well. So that's how to illustrate in using the delta rule for the Adeline network. But what we are doing here, we are considering only a linear activation network, linear activation function to update the weightage, even though the network itself has a nonlinear activation function, but in updating the weightage, I just consider the output before the nonlinear activation function, or in other words, I will just consider the network with a linear activation function, even though the network itself has a nonlinear activation function. So this is one example, one illustration of updating the weightage using a delta rule when we consider a linear activation function. I also have another example when we update the weightage here, considering a linear activation function, but we will apply that concept on a perceptron network. What is a perceptron rule? It's pretty similar to Adeline, but the updating steps of the weightage here, we compare it with the output of the network after the nonlinear activation function. So that's different. The updating for both cases, the networks are both of them with nonlinear activation function. But in Adeline, the updating step of the weightages use the output before the nonlinear activation function. So the updating, you can consider the network with linear activation function for Adeline, but for perceptron, the updating of the weightage use the real output after the nonlinear activation function. But the calculation, the nice thing in here, the calculation of perceptron still consider a linear activation function. So what do I mean by that? Let's take a look on the example here. I will use the same example here. I have an analogic function. I will use the same network here to capture this analogic function. For simplicity now, let's just consider the nonlinear activation function as a signum function. So signum function means if you have positive z, then the output of this signum function will be equal to 1. If z is positive, the output is 1. If z is negative, the output is -1. If z is 0, then the output is 0. So I will use this signum function as the activation function, and then I will update the weightage in this perceptron rule by taking into account the output of the activation function. Same like before, I will just grab the initial weightage from the air. I will just take 0, 0, 0 for W1, W2, and B correspondingly, and then same just to have a same comparison. I will just take the same learning rate here with a learning rate equal to 0.1. So let's start it. I will calculate the output of this network, but since I'm going to use perceptron rule, so I have an interest more on the output of the activation function, because this is the output that I will use to update the weightage. So I will calculate the updated weightage here by first calculating the output of this network after the activation function. So y here will be equal to the output of this node W1 times X1 plus W2 times X2 plus B, and then I will wait it for the signum of that output. So signum of this value will be equal to signum of 0 times 1. I will start it with the first data set plus 0 again for W2 times 1, the second input of the first data set, plus the bias 0. So this will be equal to 0. Signum of 0 is 0. Then I update the W1 now. W1, in updating the W's, now here, I still consider a linear activation function. So it's a bit inconsistent, actually, I admit. The Y is calculated from the output of the activation function, but updating the W, we just consider the activation function to be linear in here. So it's a bit inconsistent, but let's see if it works. So I will update the W1 now, taking the OW 0 plus the learning rate 0.1 times the target is 1 minus the current output times the first input of the first data set. So if you look at this, this is exactly what I meant. The output is calculated considering the activation function signum, but the updating of the W is not considering the activation function. If I want to be consistent, then I cannot use this approach to update the weightage, but instead I have to use the approach that also consider the activation function here, right? Because the first derivative of y with respect of W here, y involves the activation function. While for this case, for the case of linear activation function, I will just consider the activation function as not a linear function, but as a unity function. A of z is equal to z. Okay, so that's what I meant by the inconsistency in the perceptron rule here. But okay, let's take a look whether it works or not. So I update the W1, I get 0.1. I do it again for W2, the old W2 plus the learning rate times 1 minus 0, target minus current output times the second input in the first data set times 1, I got 0.1. So this will be my updated W2. Now for the bias, I do the same thing. Old bias plus learning rate times the target time minus the current output times 1, of course. It will be equal to 0.1. So at this iteration, my W1, W2, and B are 0.1, 0.1, 0.1 correspondingly. I continue the update because I still see an error there. The target should be 1, but currently the output is 0. So I continue the update here. The second step, then I will use the second data set. I calculate the output of this network. It will be equal to signum W1, my current W1 is 0.1, times the first input 1 plus 0.1 for my new W2 times the second input minus 1 plus the bias 0.1. It's equal to 1. Signum of, it will be equal to 0.1. Signum of 0.1, because 0.1 is a positive number, it will be equal to 1. So the y value now it's 1. I will update the W1 now. I will use the same equation. The current W1 is 0.1 plus learning rate 0.1 the target is 0.1 now. Sorry, the target is -1 now. I subtract it with the current output 1 times the first input 1. It will be equal to -0.1. I do it again for W2 with the current W2 0.1 and the input -1 for X2 here, I will get 0.3. I do it also for B for the bias, and then the updated bias is equal to -0.1. There is still an error, as you can see here. The target is -1, the current output is 1, so I continue update it. In the second iteration, I will use in the third iteration, sorry, I will use the third data set here. And then after my calculation, I will get the updated W1, W2, and B equal to this 0.1, 0.1, minus 0.3. If I calculate the Y, apparently there is still an error, so I will use the fourth dataset to update the weightages even further. I will get this 0.3, 0.3, 0.1. You can check it by yourself. Apparently, these weightages are not converged yet. So there is still an error. Y is still not equal to T. So what I'm going to do next, I take the fifth iteration again. I use back the first dataset for the fifth iteration. And then I do it again. Apparently, it's still not converging. I do it again, until after I check the Y, the output Y is consistent to the target T. That apparently I achieve it after the 10th iteration, in which after I tried for the 11, 12, and 13 using the other data set, the weightages are not changing there. So it's converging because the output Y is equal to the target. So the error will be equal to 0. When the error is equal to 0, T minus Y will be equal to 0. So there will be no updating effort anymore. That's why W1, W2, and B in the last 4 iteration will keep constant. So this will be the optimal W1, W2, and B in my perceptron network here. So I will use this. I will calculate the Y using this expression, and then I got a nice result here, where Y1 basically here in this table is the output of this node before the signum activation function. But it seems that a perceptron works. We get the optimal weightage there, despite the inconsistency that I mentioned before. But from what we learn here, it seems that perceptron takes more iteration steps compared to the Adeline in here. I don't know, probably it's because Adeline is more consistent in the sense it calculates the output before the activation function, and then it also uses the linear activation function to update the weightages there. I don't know, but Adeline seems to give a faster iteration to get the weightage converged. So these two networks, Adeline and perceptrons, will give us an illustration on how to use delta rule with gradient descent method, considering a linear activation function. Even though once more I want to mention here, even though the network itself has a nonlinear activation function, but the updating step here, we consider the activation function to be linear. Both of them actually, to me, even though perceptrons is more inconsistent compared to Adeline, but both of them actually is, to me, both of them are not really consistent. When you want to update it, when you want to update the weightage, you have to consider the nonlinear activation function mathematically. But it seems Adeline and perceptrons, both of them, also work very well. In the next few slides, I will discuss the optimization of the weightage by considering the activation function. So we are going to consider the activation function, the nonlinear activation function, also in updating the weightages. So let's consider again a simple single net like what we did in the previous few slides, but we are going to use the following activation function, this nonlinear activation function now. In such, the output of this single net y will be equal to this function for the input that is coming from the output of the node. So this function for z equal to w0 plus w1 times x. In such, then the output, the y here will be equal to 1 over 1 plus exponential of minus w0 plus w1 times x. Now, let's evaluate the first derivative of a with respect to z, the derivative of the nonlinear activation function with respect to the input here. If we have this nonlinear activation function, if we have this function, apparently the first derivative of this function will just simply look like this. The first derivative of a with respect to z will be just equal to a of z times 1 minus a of z itself. You can try to check it by yourself. It is easily proven. You can just try to differentiate this function with respect to z, then you will get this, and this basically is equal to a times 1 minus a. Okay, now we are going to consider a single net with this activation function. When we are going to update the weightage in our net here, like what was suggested by gradient descent method, the iteration when we want to update the weightage, we just simply use this technique. The new weightage, the updated weightage, will be just simply equal to the old weightage plus a certain updating factor, where the updating factor is equal to minus the learning rate times the first derivative of the error with respect to the weightage that you want to update. Where error here, as we have already discussed many times, is for simplicity, it's always expressed like this: half times t, the target, minus the output of our network squared. So when we are going to evaluate this updating factor, this what we will get. Error is this half times t minus y squared. We are going to differentiate this with respect to w, where w appears in y. Y is a function of w. So by using a chain rule in the differentiation, you can see that the first derivative of e with respect to w will be the first derivative of this with respect to t minus y which will be equal to t minus y, so, right? And then the first derivative of negative y with respect to y, which is -1. It's just a chain rule. And then the last one is the first derivative of y with respect to w. So this will be the uh, equation to express the first derivative of e with respect to w. Now we can uh, substitute this value by, because we know that y here is equal to a function of a when the input is equal to z. So the first, again using the chain rule, the first derivative of y with respect to w, then it will be equal to dA, dz, dz, dw, right? Let's just follow this because y is equal to a z and z appears as a function of w. So dy dw will be equal to dA dz times dz dw. Since we already derived what dA dz is from here, so I can just simply substitute these to the first derivative of a with respect to z here, and then at the end I will end up into this expression. Okay, this looks a bit more complicated when compared to the Adeline and perceptron rules. It's because we will consider the nonlinear function in here. Okay, and then next, therefore, the updating factor of w, then it will be just simply negative alpha times this one, which will be equal to alpha, the learning rate, times all of these terms. Okay, and of course, then if you want to update w naught, then you just simply use the old w naught plus these, all of these terms times the input of the bias, where the input of the bias then will be equal to 1 here. If you want to update w1, will be just simply the old w1 times plus these terms times the input of the w1, which is x in our case of a single input simple net in here. Let's again we take a look on the AND logic function here. But just to play around with the number here, I will consider a unipolar value here. So the output are 0 and 1 here. But now in updating the weightage, I will consider also the nonlinear activation function in here. So first, same like what we did in Adeline and perceptron, I will just take weightages from the air. For simplicity, I will just take 0, 0, 0 as the initial weightages, and then I will just take the same learning rate equal to 0.1 here. So in this case, then the output y will be equal to the output of this activation function. We will use this activation function times the output of the node here. I will have to input here, of course. Here I have x1 and x2 here. So I just calculate the y, the w1 for time being is 0, w2 is 0, b is 0, and then the input x1 and x2 are 1 and 1. So I will get 0 when I calculate this activation function for z equal to 0, then I will get 0.5. So 0.5 is the output now. Then I will update the first weightage, W1. I will do the same thing. I will use the old weightage, 0, plus the learning rate, 0.1, times t, the target is 1. The current output is 0.5 times 1 minus az again here times the first input x1. So this just follows the updating function in the previous slide. Please take a look here. If you compare this to Adeline and perceptron, we have this term where this term is coming from the nonlinear activation function, which to me, this makes more sense. This is more, looks to be fair than Adeline and perceptron. We are taking the output after the nonlinear activation function. Obviously, intuitively, to me, to make it fair, the updating of the weightage, I should also take the nonlinear activation function into account. Okay, and then now let's update the W2. Same thing, I take the old W2, 0. I use the same learning rate, target and output because we are still looking at the first data set there. Then I multiplied by the second input on the first data set times 1. Then this is what I will get, 0.0125 for W1 and W2 respectively. For B, I do the same thing, and then at the end I will get the same number, 0.0125. So now at this first iteration, the weightage W1, W2, and B, all of them are equal to 0.0125. I still see an error here, right? The target is 1, the output is 0.5. So I update it again using the second iteration, but now my current weightages are 0.0125, 0.0125, and 0.0125. And then I use the same technique again here, but I will use the second data set, 1 minus 1, 0, the second data set here. So I will just calculate the output of this network using this input, 1 minus 1, and then after I calculate it using this nonlinear activation function, I will get the output y is equal to this 0.6514. And then I will update W1, W2, and B accordingly. But now, of course, I will use the old W1 from here, from the first iteration. And the output now is the current output 0.6514, where the current target output is 0. And then the new W1 will be equal to this, minus 0.0023. I do it again for W2. And then same like what I did before. And then I do it again for the B. So these are my new W1, W2, and B. I still see an error here. I got 0.6514 where my target is 0. So I take the third iteration with the new weightage W1, W2, and B there. I calculate again the Y for the third data set, minus 110, and then the output from this net is 0.7966. I update the W1, W2, and B. These are the values that I will get for the weightages. I still see an error again here, 0.7966, where it's supposed to be 0. So I will take the fourth data set to update it further. You can check it by yourself. I will do same calculation again here, but of course I will use the updated weightages to update again the weightages in the next iteration. So you have to do it repetitively until it is converged. The next step now here, what we have already considered up to the previous slide, we were just considering a simple single net. But in real practice, when you want to capture a complex signal, you want to capture a complex function, you might have more than one neuron, more than one layer, so you might have a complex network here, more than one nodes. So let's take an illustration here where I have a complex network that looks like this. In this case, I have two layers of networks, yeah, where the first layer I have three neurons, and the next layer here I have two neurons. And then this system will have four inputs with two outputs. Okay, before we move further on discussing on how to optimize all of the weightage here, we have a lot of weightage just here, right? We have a lot of line here to connect one neuron to another neuron. So we will have a lot of weightage. To have a same language on discussing about which number is which weightage referring to which net, then let's agree on this notation. So if I write W with subscript J, comma, K and a superscript of L, that means I'm referring to a weightage in the neuron number K, in the layer number L minus 1, that is connected to the layer L to the neuron number J. Wow, looks complex, but I can give this illustration. So if you look at this and this net, I will assign the weightage in this net, in this connection, to be W subscript of 2.1, 2,1 with a superscript of 3, which means this is a weightage in the first neuron. The K here is 1. So this is the weightage in the first neuron. In the L minus 1, L is 3 in here. So 3 minus 1 in the second layer. This is first layer. This is second layer. First layer is the input. Second layer is this one. So this will be the weightage of the first neuron in the second layer, where second layer is coming from 3 minus 1. That is connected to the second neuron in the L layer, in the third layer. Okay, so that's how, let's agree on this notation. W 2,1 with superscript superscript 3, then in here means the weightage of the node in layer 2, the first neuron that is connected to the second neuron on the third layer. Same thing to the bias, but bias is not connected. It's not connecting to neuron here, to nodes here. So for bias, we can just give this indication: B subscript J superscript L, which means this will be the bias in the network number J in the layer number L. So for this one, then I will have B with subscript 1, neuron 1, L, the superscript 2. So it will be B1, 2. Okay, let's agree on this notation. Now the question here, we might have a lot of weightages here, right? How to optimize all of the weightages? The concept is still the same. We will optimize it just like what we did in the previous step by considering the nonlinear activation function, but it might involve more than one layer. It's not like what we did in the previous example when we only deal with a simple single net with one net, a layer only. To start, let's take another simple case here. It's slightly more complex than a single net, but this is still simple. So I have 1, 2, 3, 4 layers, but each layer only has one neuron. Obviously, then here we have, let's just assume we don't have bias to optimize here. So we only have 3 parameters to optimize, W1, W2, and W3 here. So the output Y of this network will be equal to X times W1. We only have one input here, X times W1. And then through this node, then we have to pass it through the nonlinear activation functions. Let's take this case as our activation function. So the output of this node will be equal to the activation function evaluated for z equal to w1 times x. So it will become like this. And let's call this value equal to a1 now. And then we have to go through here. We have to multiply it by W2. So at this point, before we enter this node, we have a value of W2 times A1. And then after we pass through this node, then this W2 times A1 will have to be evaluated for the activation function. So the output of this node, then it will be equal to the activation function A evaluated for Z equal to W2 times A1. And then multiplied again by W3 evaluated for the activation function. And then the output here, A3, which is the activation function value for Z equal to W3 times A2 is the output of this network. So it's equal to Y. And then let's assume again, like what we did previously, we are going to use this network to model a certain of data where the target is equal to T. So for the optimization approach, we have to minimize the error respecting this error function. That simply compare the target value T with the output of this network Y. The objective now then, we are going to optimize W1, W2, and W3. Like what we did before, let's start it from here. Once we know the Y, when we are going to update W3, what we have to do, we have to update it with the updating factor, right? Delta W3, where the updating factor is dependent to the first derivative of R with respect to the corresponding weightage W3. To be precise, then the updating factor will be the delta W3 will be equal to minus alpha, the learning rate, times the first derivative of E with respect to W3. But we know already from this schematic diagram that error which appears as a function of y here, we know that y here is a function of a3, while a3 is a function of w3. So the first derivative of error with respect to w3 will be equal to the first derivative of error with respect to a3 times the first derivative of a3 with respect to w3, right? It's just a chain rule. And then if I can write it, then the first derivative of error with respect to a3, I can rewrite it into something like this, right? Because the error with respect to a3, where a3 is equal to y, basically, so the first derivative of error with respect to y will be equal to negative t minus y. So using this updating factor, minus alpha, the learning rate, times this value, we can update the W3 in the first iteration. But we still need to update W2 and W1 as well. So what we are going to do to update the W1, again, we know that the error here appears as a function of A3, while A3 is a function of A2, right? And A2 is a function of W2. Again, I repeat it. The error here is a function of y. And y, if you look at this, basically is A3. And A3, if you look at this, A3 appears as a function of A2. And A2 is a function of W2. So the first derivative of error with respect to W2, we just apply the chain rule. It will be this one again, a negative t minus y, which basically this is the first derivative of e with respect to a3, where a3 basically is y, times the first derivative of a3 with respect to a2 times the first derivative of a2 with respect to w2. So we can calculate all of these things, and then we can have this value to update our W2. Moving to W1, it's the same like before. We know that the error here, which is a function of y basically is A3, A3 appears as a function of A2, A2 is a function of A1, and A1 is a function of W1. So using chain rule, then we can also find the first derivative of e with respect to W1 to update our W1. The nice thing, if you look at this, for W1, the first 1, 2 terms is equal to this term also. So what you have to do, actually, you have to calculate it in backward. After you calculate this, you get this value. This value best, you can use it again in the next iteration to calculate the subsequent W. And then if you have more than 3 W's, then you have to do it iteratively. Yeah? So we just update this, actually update the last. You just have to calculate the last term here to calculate the first derivative of e with respect to corresponding W. This is a technique that we call as a back propagation, because we update the W, the weightage from the last one, W3, W2, W1, because of this convenience in transferring the value that we calculated before. So in short, then the optimization comprises 2 steps. The first one, you have to do forward calculation to calculate y. So we calculate y by taking the X, and then using the initial guess of W1, calculate the output of this node using initial guess of W2, we can get the output of this node multiplied by W3, and then at the end we have Y. We have one shot of forward calculation. And then after that, we do the backward calculation to update our W's from the last one. That's why we call it backward calculation in there. That's the reason, as I have already mentioned, why we call this technique as a back propagation. Let's refer back to this multi-layer, multiple neuron. We have 3 layers and we have different number of neuron at each layer there. So the concept is the same. Either you have one neuron at each layer, the one that we discussed in the previous slide, or you have more than one neuron at each layer. The concept is the same. The difference is only the error that you have to take into account when you want to update the weightage. You have to consider the error on both output here. Why? Because one weightage, let's take one of the weightage in here. This weightage will contribute to this error, but it also contributes to this error. This weightage will contribute to the output Y1, but it will also contribute to the second output of Y2. Okay. Therefore, when you want to optimize, let's say W4, 3 of 2, that means, again, I like this. This means then the weightage of the fourth neuron in the first layer, 2 minus 1, first layer, connected to the third neuron on the second layer. So basically it's this one. If you want to optimize it, then you have to calculate the first derivative of the first error of the first output with respect to this weightage, as well as the propagation of the error, propagation to the second error, the error of the second output to the corresponding weightage. Let's take a real example here. This will involve a lot of calculation. So I want to suggest to you, get ready with a pause button. You might need to pause it, check the calculation with your calculator, and then you can follow the optimization of this weightage in this complex multi-layer network like this. So in here, I have 2 inputs, I have 2 outputs. There are 3 layers, and at every layer we have 2 neurons. That means then how many weightages do we have? 1, 2, 3, 4, 5, 6, 7, 8 W, and we have 1, 2, 3, 4 bias. We are going to calculate. We are going to optimize all of them. First, we take just the initial. These are the 2 inputs, x1 and x2, and apparently the target output are these two, 0.01 and 0.99 here. And then at the beginning, I will just take initial guess for all of the weightages here. In here, I just take a random number. I don't take all 0 values here just to make the demonstration of the calculation be more apparent there. So all of these weightages are initial guesses, but these are the inputs and these are the target outputs. So the first step, then we have to calculate the output in forward manner. we take the forward step. Let's do the forward calculation. So first, I will calculate this part. This point, the output of this node, then this node again is equal to x1 times w112 plus x2 times w212 plus b12, right? That will be the output of this node. Please check it. Check the values that I have already provided. The output of this node will be equal to this 0.3775. Now I move forward again. I will calculate the output from this activation function using this input Z12. So I use this activation function, and then this is what I will get. The A12 again, please be careful. 2 in here doesn't mean square, but this to indicate the layer number. So the output of this activation function will be equal to 0.59327. Then I do it again for this node. I calculate it. The result is 0.3925, and then I calculated again the output of this activation function, and then this is the value that I will get, 0.59688. I move again to these two nodes, calculate it again, your Z13 and Z23. Then from there, you calculate the output of the activation function. You will get A13 and A23, where basically this A13 is your Y1, A23 is your Y2, right? Please check all of these values, whether I calculated correctly or not. If I made a mistake in calculation, it might be, but the concept is what I want to deliver here. So we have already done the forward calculation. I calculate the output of this network, Y1 and Y2. These two values are not equal to the target value. Still remember, the target value is equal to 0.01 and 0.99. So definitely there are errors here there. So what we have to do, we have to update the weightages, all of the weightages, all of how many was it? 8 weightages, and for bias, we have to update them all. So these are the initial guesses of all of the weightages and the bias. We calculate in a backward step now. First, I will calculate the error here. I have two errors because of the first output and the second input. The total error will be like this. You can just calculate it. You just sum them all to get a representative of the total error. We have a certain number of error here. You can do it by yourself. And then we need to update the weightage one by one. So we started with the last layer because we have to move in a backward way. We started from the last layer, and I will start it from the first neuron. From here, we will update first for this weightage. What is the effect of this weightage to the output, the total output? So definitely it agrees with what we discussed before. The total output error then will be equal to the error of the first output and the error of the second output. But if you look at this network, let's go back here. If you look at this network, the W113 is not contributing to the second output, right? W113 only contribute to the first output. So in this case, then this part is 0. W113 is not responsible to the error in the second output. So for this one, we just need to calculate the effect of W113 to the first error. So if these are indicated as Z13, the output of this node, and these are indicated as A13, the output of this activation function, then the first derivative of the first error E1 with respect to W113, it's just a chain rule again, will be equal to the error with respect to A13, which basically A13 is Y1. So this part basically is equal to minus T1 minus Y1, right? Minus between bracket T1 minus Y1 times chain rule again, the first derivative of A13 with respect to Z13, right? Times the first derivative of Z13 with respect to W113. Okay. So because the expression of E1, the error one, is like this, the first, as I have already discussed just now, then you can calculate the first derivative of E1 with respect to A13 easily. It will be like this, right? We have already discussed just now. And then the second term here, we have to take a look on this function. A13 appears as a function of Z13, right? Z13 is the input of this activation function. The first derivative of A13 with respect to Z13 will be equal to AZ for this Z times 1 minus AZ for this Z. So it will be like this, right? And then the last one here, the first derivative of Z13 with respect to W113, we just have to come up with the expression of Z13 as a function of W113, which is this one, right? What is this last two terms? Last two terms is coming from the previous layer and the second neuron, and the last term here is coming from the bias. But these two terms are independent to W113. That's why the first derivative of Z13 with respect to W113 will be just simply equal to A12. So you calculate this value and then you can update the W113 using this value. Just considering the learning rate, so you have to update it with minus alpha, the learning rate, times this value. And then you can update the W113. If I calculate it properly, then this will be the updating factor of W113. Now we have to do it again for W213, W123, and W223. Luckily, again, all of these weightages for W213, let's say, it only contributes to the first output. So the effect of the second output with respect to W213 is 0. For these two, W123 and W223, both of them only contribute to the second output. So the effect to the first output to the first error will be 0. You can do exactly the same like what we did in the previous slide, and then you can find the updating factor for W123, W213, and W223. This is supposed to be 223. Okay, we finish updating all of the weightages in the last layer. Be careful here, you also have to update for the bias B23, B13, but basically it's also the same, even though moreover actually the equation will be much simpler in that case. Now we move to the next layer after the last layer, to the layer 2. We are going to update the W112. But W112, if you look at this, it contributes both to the first output and the second output, right? So none of these two terms will be equal to 0. You have to calculate both of them. So the first term, I can calculate it like this. E1 is a function of A13, where actually A13 is Y, but A13 is a function of Z13. Z13 is a function of A12. A12 is a function of Z12, and Z12 is a function of W112. So you substitute all of the value, all of the function here, and then you can get this part. The first derivative of first error with respect to W112. And then for the second term here, it's the same. The first derivative of error with respect to W112. The error actually is a function of Y2. Y2 actually is A23. So A23 is a function of Z23. Z23 is a function of A12. A12 is a function of Z12. Z12 is a function of W112. So you can also calculate this, all of them. You sum these two, calculate each of them, you sum these two, and then you will get the updating factor for W112. You have to do it again for, let's say, W122. None of this term can be neglected because W122 contributes to Y1 as well as Y2. So you have to calculate them all. The first derivative of the first error with respect to W122 is equal to this term times, because A13 is function of Z13, and then Z13 is function of A22, A22 is a function of Z22, and Z22 is a function of W12. So again, another chain rule here. You do it again for the second term, the effect of W122 to the second error, and then you will get, after you sum it, these two, you will get the updating factor for W122. You do it again for W211 with the same techniques. W211 contributes to both of the outputs here, so you have to calculate both of them accordingly. After you sum these two results, you will get the updating factor of W212. The last one, you still have to do it for W222, which also contributes to the two outputs. So you have to calculate both terms correspondingly, and then you will get, after you sum it, you will get the updating factor of W222. Okay, if you calculate it, if I calculate it properly, please check it. This will be a, well, rather tedious calculation, but I suggest you to check it. After you calculate it, you will get these values. And then these are the values to update the updating factor for all of these four weightages. Okay, so that's why we call it as back propagation, because after you move forward, then you propagate backward to update the weightages. I want to remind again to you, don't forget you have to do it also for B12, B13, B22, and B23. Okay, and then after one iteration, up to this point, we only do it for one iteration. After you get all of the weightages updated, you calculate the output. If the output still doesn't agree with the target, you have to update again all of the weightages with the same steps. If it still doesn't agree, you have to update it again, iterate it again many times, until you converge to the target. Okay, so what I just shared with you in the last few slides here is just an illustration to update in one iteration. You have to do it many times until the output converges to the target. If I calculate it properly, again, the updating factor for all of the weightages except the bias, the calculating for the bias is relatively simpler. So all of the updating factors for W, all of the W's here, all of the 8 W's here will be like you can see in this slide. Again, please check it. When you check it, you will also have a sense on how the calculation will be made. So in a complete form, then the updating function incorporating all of the updating factors will look like this, where alpha here is a learning rate. You are free to choose that. If it is too large, you might skip the optimal value, but if it is too small, it might take more time to converge.